He's a principal scientist for Computer Science Corporation right now, and he's interested in amateur astronomy, has, among other things, developed low-cost, very light mirrors for portable observing. And Dr. Chen, I did want to mention that there is a team from the University of Arizona that's developed a composites, very easy to mass produce mirror that perhaps if you have a chance to talk to them, you'd be interested in what they've done. Okay. And in the field of professional astronomy, he's developed a number of instruments and carried out many experiments and participated in major research efforts. In space science, he developed, built, and programmed the ultraviolet imaging telescope, and many of us will remember seeing the flights on NASA Select that took place. There were two, one in 1990 and then a recent one in March of 1995. And during that flight, he was part of the mission control group at NASA Marshall Space Center, and he conducted real-time operation of the telescope in orbit. And in space instrumentation, just briefly mentioning some items, he's developed charge-coupled device detectors, dedicated microcontrollers, gamma ray detectors, and in ongoing work, he's invented a lunar telescope, which we'll be talking about today, a robotic lunar telescope, charge injection devices, ultralight optics, ultraviolet imaging data analysis methods, and next generation space telescopes. And he has a number of hobbies, including Tai Chi, and I have a friend who's a student of Tai Chi, and I'm very interested in that. So please do welcome Professor Dr. Peter Chen.
Thank you. There was an inspirational talk by Dr. Borowski, and I find it very interesting. I really like it. And I think it's gratifying to know that there are still people around who has visions and dreams for this kind of this space project. The approach that I myself and my colleagues are taking is somewhat different. We think that it's all complementary. We think that in the current climate, it is necessary to get things going, just to build the momentum, so that we can all visualize space settlement, lunar colonization, and so forth. This is a progress report on the lunar telescopes that my colleagues and I are developing. Our goal is to demonstrate that we can build telescopes that are ready to go to the moon within the next 3 years or so, and that they can be not only is it affordable to NASA before its budget cuts, but it's actually getting to a point where individuals and institutions can finance it. With this project started off about 5 years ago when a group of us got together and say, hey, we'd like to see telescope on the moon, but nothing is likely happening for quite a while. Let's do something about it. And we have been working on our own for the last 5 years, and we have made really a great deal of progress. Thank you. We're gratified to say that we have made enough progress to convince NASA that this is what we're doing is actually not such a far off, not such a wild dream after all. And we were recently selected as one of the new mission concept studies for the National Space Mission for the 21st century. This is very gratifying because it shows that we're on the right track. But more important enough for us, we now have some resources to do the work right, instead of having to bootleg stuff and cards and paying for colleagues. I guess the main point here I'm trying to get at is that even despite what you see daily in the newspaper about NASA cutbacks and reorganization and everything else, there's still a lot of things that can be done that doesn't require too much in terms of budgetary stuff. And space science is still a lot of fun. Oh, exciting. Okay, now, when we talk about space telescopes, lunar telescopes, this is the kind of thing people usually envision. And I guess this is the kind of thing Dr. Borowski was talking about. It is very inspiring, and we would love to see that happen. The reality of the situation, however, is that it's not going to happen anytime soon. The main reason, of course, is that you can see the size of those kind of things. It's this is an size of telescope we're talking about, this is kind of thing. The truth of the matter, of course, is that we certainly do not have the capability to put that kind of payload on the moon anytime soon. And it is going to cost an arm and a leg. You are talking about billion-dollar class projects here. The other thing, of course, is that it's not, the reason why it doesn't happen soon, of course, is that how are you going to get something very big up there? We can't get it, therefore the general the thing is that, well, hey, we can put it up in pieces, we can go and assemble it. Or better yet, we go up there, we send somebody up there and get the lunar material and build it on site. When you talk about getting people on and getting fancy robotic materials on the moon, that is the kind of thing that takes about 10, 15 years and will cost you $10 to $20 million. And even if Congress and the President change their mind tomorrow and decide to say, okay, you guys go to the moon, you can have all the money you want, do anything you want, you will still take 10 or 15 years. As my friends in the space business like to say, quality takes time, and some things will take 9 months, no matter how many men you put on the job. So what we're trying to do is a little bit more modest. Instead of large telescopes, we're thinking about smaller ones, about 1 meter size. So it's a respectable size. And instead of having men assemble and establish a lunar settlement there, we'll say, hey, let's do something quick and dirty in the meantime. Let's put something small, reasonably small, that can do the job, that can generate the science return that we want, and that we can do quick and dirty cheap. And so this is what I'm talking about. I guess I should say one word about my format of the talk. I see that I'm scheduled for an hour or 45 minutes at least. I can't imagine talking that long, and it's not a matter of getting the audience asleep. I think I might fall asleep myself. So I'll try to get the presentation over quickly, and then I'll try to give a demonstration, show you some of the stuff that we have made, and give you a demonstration which I hope you will find amusing. Now, let's get to the telescope. I'm an astronomer, therefore I'm interested in getting telescopes to the moon. As everybody knows, of course, the moon is a fantastic place for astronomy because it's dark for half a month. From day to night, it's 350 hours. This is in contrast to 12 hours on the Earth and 45 minutes in the Hubble Space Telescope. The fact that it is dark for a long time means that you can observe for a long time. You can go to much fainter objects. However, from the scientific point of view, there's more compelling reason than that. It's just not that it's a neat toy, but we think it is really important for the advancement of space science. The next, beyond the Hubble Space Telescope and the Great Observatory series, the next push in science, we think, will be to look for planets around other stars. We would like to see how many planets there are around other stars, especially little blue planets around little yellow stars. Okay? And for that, unfortunately, you cannot do that on Earth. The atmosphere with atmospheric compensation is a tremendously difficult problem. In space, you need something bigger than the Hubble Space Telescope. This is the Hubble Space Telescope is 2.4 meters or 94 inches in diameter. It has been estimated that if you want to do planetary detection, you need telescopes that's about 10 times bigger, about 60 meters diameter. Now, the Hubble Space Telescope costs $2 billion roughly. And generally speaking, the cost of a telescope goes up as a cube of the diameter. So it's the point is that if you try to get the money or get a project to build a 10 or 16 meter telescope, well, you don't have to worry about feeding anybody in NASA. There won't be any money left. It takes up everything. And of course, so this is not likely to happen in a short while. The other way to do it, of course, is that, hey, instead of 60 meter telescope, let us have two, say 1 meter telescope, 60 meters apart. And then we can look at the same object, we can combine the signals and feed them together and try to look for little planets or little details. This is called long baseline interferometry, or this is called optical interferometry. In order to do that, you do need the telescope that far apart and very stable. There's a big push in NASA right now. NASA has identified this as the major science objective for the next century. And there's a great deal of study right now to see whether we can do it any other way. The way that is being considered is doing things from multiple spacecraft. You have two spacecraft in orbit, you have both look at the same place, and you combine the light beam together from either source spacecraft, and they try to do this. The problem with that approach is that it is very difficult. Right now, in order to get two spacecraft going together and know their distance to within 1/100th the wavelength of light, it's about 2 orders of magnitude beyond what the state of the art can do. That is because your spacecraft is orbiting, and there's things like the spacecraft vibrates a little bit, just a tiny little bit, and then the solar wind comes by and pushes you around. And then the whole thing jitters around. You can't get the thing stable enough to do it. This is a very difficult problem, and there are a lot of imaginative solutions being suggested for it. But as I said, it is still a long ways off. And in the meantime, there's a solution right on hand. Just get the two telescopes, put it down the moon, and observe it. The moon, as we know, is a huge, massive object. The surface is covered with dust. It's seismically dead. You put two telescopes down on the ground, and they will stay exactly where you put them. They're not going to move. Therefore, this is for scientific reasons, this is the moon is the most accessible option right now to do it. This is why we're pushing for that. As I mentioned earlier on, of course, we don't see humans on the moon. We like to see it, but we don't see that happening anytime soon. Therefore, we like to put telescope on the moon that is on unmanned robotic stuff. And the immediate reaction people will come up with, of course, especially if some of you are amateur astronomers, is say, hey, we hear of all those robotic telescopes, remote control. Why can't we just get one of those telescopes, plug them down the moon, and then get a joystick and control it? Put a CCD in the back, like your video camera, and get the picture there. That actually is a viable concept. The only thing is that if you look at the details, you find out there's a lot of technical details that has to be solved. It is not quite that simple. Therefore, I'll discuss what these are. Well, putting telescopes on the moon, as I mentioned, the first and foremost problem, of course, is money. So as in everything else. By the way, this is a takeoff on the. Some of you may be familiar with this cartoon. It's a takeoff on the Very Large Array. The radio astronomers have an array for interferometry, which is, I think the dish is something like about 10 meters across, 40 foot, 50 foot across, and there are 27 of them. And they're spread over a Y-shaped track in New Mexico. So, several miles long. This is called a Very Large Array, and it's very productive. This is what we use to study quasars and QSOs and active galactic nuclei on. So the cartoon says that, well, in space, we would like to see a large array, similar array on the moon. Well, we haven't got it, so let's, I guess we end up with a little toys. That's what we can get. So that's the main problem. The second problem, of course, is weight. This is my favorite cartoon character. So a good illustration thereof. If you look at the past spacecraft mission that we had, look at the Hubble, look at the Galileo. It's about 2,500 kilograms, 5,500 kilograms. Those were, of course, they were got there by the space shuttle, which is a big, heavy lift vehicle. If you look at the vehicles that we have on hand that are capable of going to the moon, you come up with something like old Titan is about, you can lift about 1,700 kilograms, and Atlas can do about 700 kilograms. In other words, this kind of the kind of major project, the kind of telescope that we are doing, that we have been doing, simply cannot be taken to the moon with the existing launch vehicles that we have. We need to invest in development of larger rockets, and that takes time and money. As a matter of fact, most of the launch vehicles listed here are considered too expensive by NASA in current days. The Delta is about $60 million, Atlas 2 is 125. If you try to submit a proposal to NASA, say, I want to do things using $125 million, they will very politely say, well, can you come back in about 5 years? Okay. Therefore, we like to, in order to do it in the foreseeable future, we need to live with our constraints. In other words, make our payload drastically smaller, very as small as we can get, so that we can afford it. Now, the other problem One other problem with putting telescope on the moon, this is a Earth-based 60-inch telescope. This is about the size we're talking about. Is that this mechanical reliability. It goes as follows. On the moon, as I mentioned earlier on, the nighttime lasts 350 hours. This is beautiful, of course, you observe all night. It's fantastic. The trouble here is that the stars, the motion of the stars, goes through very, very slowly, about 30 times slower than on Earth. On the moon at night, its temperature is about that of liquid nitrogen, about 77 degrees K. It is way below the, I don't know, it's probably way below anything you guys see in Minnesota. And as everybody knows, what happens to mechanical stuff in cold weather. The darn thing binds and freezes and breaks and becomes very brittle. Now on the moon at 77 degrees K, you have this extremely cold condition, and then you're trying to track a telescope across the sky at this extremely slow rate. How slow? Well, if you do the calculation, you say, well, a 1 meter telescope requires a 1 meter diameter drive wheel. You work out the motion, it turns out you require motion of something like 1 micron per second. With that kind of precision movement, steady, slow movement, very precise movement, and the kind of temperature, there is nothing in spacecraft mechanism that can do it. We don't have any gears or bearings or anything that can perform that kind of duty. And also, you remember that we are not likely to get anybody on the any people, persons on the moon anytime soon. Therefore, there's nobody to maintain the telescope. Once you put it down, you better download work by itself for 10 to 15 years unattended. And people who are familiar with Operation Ground telescopes, or those of you who have your own telescopes, know what the task that is. And a third problem that we come across is radiation. The radiation, this come about because on this, the sun once in a while goes through a big solar flare, so we know that. And when the solar flare happens, it shoots a whole gigantic beam of particles, alpha and protons and alpha particles out into space. On Earth, we don't worry about it too much because we are behind our atmosphere and our magnetic field. The particles get diverted and they go to the pole and they make beautiful auroras, and that's about it. And it just disrupts communication once in a while. On the Hubble Space Telescope, it's still not too bad. You are still within Earth's magnetic field. Therefore, most of the particles get diverted. On the moon, unfortunately, you don't have that option. It's outside the protection of Earth's field. It has no atmosphere. It doesn't have its own magnetic field. Therefore, whenever a big solar flare happens, the protons wham hit the moon full force. As a matter of fact, those of you who will remember the Apollo missions would remember this was one of the main concerns. We were concerned that if a solar flare happened when the astronauts on the moon, he would be dead. And there's just no way to shoot that. Unfortunately, the kind of stuff that we're talking about, the astronomical detectors that currently use, the CCDs, or charge-coupled devices, that's the kind of thing you find in your video cameras, are extremely vulnerable to this effect. And it can be shown that it doesn't take much to cover. This is a calculation, scientific calculation. On the top is a record of solar flares. This is solar cycle and a number of sunspots, by the way. And those, the vertical lines are the number of flares and how high they got. Over the period of 1980 to 1985, this is the number of stuff we have. And the horizontal bar shows you that if one of those things happens, if you have a CCD at this point, and this guy happens, you are 100% dead. And we're talking about multi-million-dollar CCDs. These are space-flight qualified CCDs. Therefore, if you put the kind of instrument we have on Hubble on the moon, it doesn't last very long. Any one of those guys will not be up. And on the average, your CCDs will last about 4 months. People actually have thought about that, have worried about this problem, and this is why this previous view graph. They said, well, we really can't, let's shield it. Well, to figure out how to shield it, well, you need a 1 meter diameter radius of pendulum. The weight of that was 68,000 kilograms. 4 shuttle payloads. The shuttle can go up and down 4 times, just carrying the shield. Or the other thing is that, hey, the moon is lots of soil around. Why don't we just bury the instrument underground and protect it from radiation? Well, that is one of those things that's much easier than conceptually to try to get done. In order to do this, you need a hole that is about 9 feet deep, about 3 feet diameter. Now imagine taking that hole in your backyard. I mean, if your landlord will let you, or if your neighbors will let you. Okay. Now imagine doing that without machinery, without people. And especially, remember, we have a payload constraint. We can't land any heavy earth-moving machinery up there. How do you do it? And one of my more imaginative colleagues came and said, well, that's easy. Just dig a hole and blow a hole there. Just go put some explosive in there, blow it up. So the question here, of course, is that how are you going to control the size of the hole? And who's going to put the dirt backwards after you do it? Okay. So in other words, it's the idea is nice, but it's not quite that simple. Well, the idea that my colleagues have worked out is that, well, in order to go in the near future, the only way to try new technology, that is to say, use our imagination, see what we can do. We obviously cannot do things the way it has been done. So let's try to think something new. And the thing we come up with is to develop ultralight optics, use the high temperature superconductors, use radiation, develop a new type of detectors that's immune to radiation, or radiation tolerant anyway, and use new space vehicles, existing space vehicles, I would say, and innovative launch strategy. Well, let me start from the first item, ultralight optics. Those of you who have made your own telescopes know that as the telescope gets bigger, the telescope gets heavier. The reason, of course, is that you have a mirror there which collects the light. And as you get bigger, the mirror gets thicker and heavier. And as the mirror gets heavier, you need bigger structures and gears and mechanics to support it. It's getting to a point where people who have 16 or 20 inches need a 16 inch you can just carry. A 20 inch you need a truck and a trailer to move it around. And the reason, if you look at that, the main thing, everything in the telescope is dictated by the optics. The heavier the mirror, the bigger the stuff you have to support it, and then the bigger stuff, the pier you have to support the whole thing, and so on. Therefore, the secret is to try to make the optics as light as possible. And here we go back to basics. If you look at the mirror and you ask them, what does the mirror do? The answer is the mirror collects light and focuses it to a point. And then you ask yourself, what is collecting the light and what is focusing the light? It is not a big piece of glass mirror. It's a little thin piece of aluminum in front. The aluminum is less than a micron thick. That is what's collecting the light. The mirror just keeps it in shape. Now on the moon, you see on Earth we have to do it differently because we have to worry about temperature changes during the day, we have to worry about wind. On the moon, it's a perfect vacuum. What's stopping you from just using a very thin piece of aluminum? You just put it out there and you stay there. So in other words, if you can make optics, they will be as thin, as small as possible, and be stiff enough to hold its own figure. Then on the moon, you work perfectly fine. So this is what we're developing. The technique actually is not that new. It's, we use the technique of replication. Normally, as I said, of course, you start with a big piece of glass, you grind it down, and you coat it with aluminum. The trouble with that approach is that you can only make this, there's a minimum thickness of this glass you have to go with. Sooner than that, when you start pushing down it, the thing bends and warps out of shape. And the way we do it, it's not such a new concept. Is to use a piece of glass with a reverse shape, and then you apply something, you put on something which is soft and pliable on top of it, and then you cure it, and then you just take it off. In other words, you're using this kind of mold to make very thin objects. This is called replication. You're reproducing that thing. This is not such a brilliant idea. I thought it was brilliant when I first walked out. Hey, this is great. And then I looked up over the literature and found that NASA did it back in the 60s, in the pioneers. This is how their mirror was made at that time. And the only difference was that the reason why they abandoned their approach was that the material available at the time wasn't good enough. Nowadays, however, things have changed. We have much better material available. And the proof of this concept is that the Europeans are actually using this method to make mirrors for the X-ray multi-mission satellite that's due to go in orbit in 1999. They have already done this for X-ray stuff. Therefore, we are adapting the technique to use it in optical. And the problem is slightly different, and we think we have better material. So this is the kind of stuff that we have made at Goddard. This is a 16-inch mirror. This is 8-inch. This is 8-inch supported by a piece of shuttle heat pipe, which is very lightweight, very insulating, and very stiff. And this is a telescope that we made. Just to show you what kind of things we're talking about, here is a picture of this guy here, this fellow here. I'd like to show you the telescope. Here's a 16-inch telescope with the support primary mirror, secondary, tertiary mirror. It weighs slightly under 3 pounds. And on the right hand side, we have a little two-month-old kit. We just like to show you what kind of weight we're talking about. And just to show you that, well, actually, the funny thing about this is, we have a hard time finding a cat that will stay still. Anyway, there's another picture of the same setup just to show you that it's not fake. It's that here are my twin daughters holding a mirror and holding the cat. You can see the cat's getting a little antsy by the stage. Okay, so one thing, the first thing we do is to develop ultralight optics and make the telescope extremely light. How light? I'll come back to that a little bit later on. The second one is the mechanical constraint. How do you point and track the telescope? And for this, we developed what is known as a high-temperature superconductor barrier. Those of you who may remember the excitement in the world that was about 7 or 8 years ago, when physicists discovered these high-temperature superconductors. That's to say, superconductors that can work at above liquid helium temperatures. There's intense work going on in this field, and they're still trying to improve it so they can be commercialized. But what we'd like to point out is that this kind of high-temperature superconductors have an extremely interesting effect that is not seen before in other materials, and that makes them extremely good, just right for making telescopes on the moon. I'll explain a little more in detail in my demonstration. Anyway, the idea of superconductors, so I got together with my colleagues at the University of Houston, Texas Center for Superconductivity, and we outlined a problem, we discussed our requirements, and they built a superconducting barrier for us, just to show them. This is a demonstration model to show that it works. And the third item, of course, is the detectors. We went and did a study, and we found a new class of detectors similar to charge coupled devices, but they operate differently. They're called charge injection devices. They are not terribly new. They were invented by GE back in 1972. However, their full potential weren't exploited until about 2-3 years ago, when the military wanted to do something, needed something that can resist against radiation. And so the SDIO folks spent a lot of money into it, and the Los Alamos folks spent a lot of money into this. They were doing bomb testing, things like that. So they want something that can stand the radiation. And so as a result of this work, this charge injection device, CID architecture, was become much better developed. And what they have developed is now available for commercial and space use. So we are working with the manufacturer to develop devices that we can use for our purpose, that to say, to go on the moon for a long time and not worry about solar radiation. The picture on this right shows the CIDs are so radiation hardened that it is one of their uses is to put the end of a broomstick and stick it inside a nuclear reactor, and to check what the condition of the rods are, and also to look at storage power to see if anybody has been cheating and stealing rods. And the work at Goddard so far is that we have worked with the manufacturer to make prototype units for us, the kind of thing that, or the characteristic that we want. This is a commercially available CID camera, and this is a set of space-like electronics that we have developed for that purpose. Well, I mentioned earlier about making a lightweight telescope and the payload as light as possible. How light? Well, that's the kind of thing we're talking about. We figure you can make a 42 centimeter diameter telescope, 16-inch. It's small, but it's not that small. The IUE, International Ultraviolet Explorer, and the shuttle flights that I work on are all the same class. If you put everything together, like a meteorite shield, you work on something around 50 pounds. In other words, we can shrink a telescope instead of say 500 to 600 pounds, we can get it down to about 50 pounds. And when you get the payload down to this low, you don't need a gigantic rocket to take it up to get on the moon. You can use a tiny ISDC rocket. This is Pegasus. This is the kind of thing we're looking at. It is a little rocket that you can make it very little because it goes up on an airplane. The airplane releases, just flies off. Therefore, you don't have to spend energy going through the atmosphere.
What's the time frame on the inside?
I'll come across that. Thank you. Here's another picture of the. I think they're flying upside down. Right. Okay. Yeah. Okay. So this is another picture of the Pegasus just before release. I thank you for the question about the tracking discipline. And the neat thing about this, of course, is that. As Dr. Borowski said, with a big lift rocket, you can go to the moon in 24 hours. With a medium lift rocket, where you go on Earth orbit and go around a couple times and then go to the moon, the way the Apollo people did, it takes about 3 days. If you do it that way, if you remember my view graph earlier on, you only have a payload of something about 50 kilograms, which is not enough. Okay, we've got a telescope, but we need the rest of the spacecraft too. And so a colleague at Jet Propulsion Lab worked out a new way of doing things. A trajectory is as follows. You launch from the Earth, apparently misses the moon. You pretend to get a little bit of swing by there, get to this point, it's about 1 million miles out, 1 million kilometers out. And then you apply just a little push. And then the rocket will come back here. And then at this point, you give it another tiny little push, and it goes into lunar orbit. This way, you can see you launch at 12:22, it gets there at 5:11. It takes almost 6 months. It takes much longer than, say, 3 days or 24 hours. But the advantage here is that now you increase the payload. Instead of 50 kilograms, you can go about 120. So in other words, you now have enough to get it done. You now have the capability of carrying a telescope to the moon with the Pegasus. Of course, it's a long time. But remember, this is unmanned robotic stuff. We don't have to worry about life support. We can take as long as we want, as long as we get it. Well, the cost estimate we have is about building a 1 meter telescope, everything included, will be about $15 to $30 million. In other words, it's about, instead of a, say, $10 billion class project, we're now talking about small explorer class projects, which is the smallest type of thing that NASA supports. This type of cost is affordable even with the current NASA budget. Another possibility, of course, is that if you look at the Keck telescopes, which is built by University of California at Hawaii, it's a ground-based 10-meter telescope, and it was financed by the Keck Foundation. It cost about $70 million. So in other words, we're getting to a point where even the private individuals and the foundations can do it. So if anybody knows, is a good friend of Bill Gates, put it in the for us. We'll promise to put his name on it, and it's Bill Gates Memorial Telescope. So in conclusion, we think we have demonstrated that it is possible to build telescopes in the near future, within 3 to 5 years. We can use a very small launch vehicle, and we can use existing material and technology. And the way we envision that thing going is that you can use a small rocket to put a telescope, 1 meter class telescope down here, and you can, as you learn, you can go along, you can start putting a bunch of telescopes down here, and they can look at, they can, in the first time, at first, they can be individual telescopes, individually controlled, and doing different things. That will make astronomers very happy because now you have a whole bunch of telescopes to work with, instead of everybody fighting for down the big ones. And then as we gain more experience, we learn how to phase them together, and we can do a interferometry array on the moon, and we can start doing a systematic search for solar type stars.
How are you going to land them with their perfect drive?
After those telescopes will have a certain small amount of mobility. In other words, their feet has to be a little robotic. You have to be able to skip a few steps and get in place. We hope to land in the right place like that. The other possibility, of course, is that with a Pegasus, $35 million, you can land one. If you really want to go on and go to a Delta, which is $60 million class, you can figure that you can put a lander on it, and the lander can carry 4 or 5 telescopes. Therefore, you can land them on Mars. It's a man, therefore, on the hand, this is a repair crew coming in. This concludes my presentation. And I would like to now show you a sample of what I'm talking about. Well, I think it'll be easier to people who can just come up and look at it.
Someone told me we'd like to move people up.
All right. Two things I'd like to demonstrate. One, of course, is the flyweight mirror. I did bring a 16-inch around because we're in the process of building one, and we expect to have a working telescope on the way in about a couple of weeks' time. Working model. But in the meantime, here's a sample of what the thing looks like. You can pass it around. This is made of a new type of material. It's not graphite epoxy. It's called cyanic ester resin. And we have been able to reproduce the figure, and we have been able to reproduce the. I thought it was there's a fishing line. Sorry. We have been able to reproduce the surface, finer, smoother of the Hubble Space Telescope, and we think we can do it about another factor of 5 better. So it is necessary, by the way, to make the figure as smooth as possible, so that you can get rid of the scattered light when you're looking for planets around the sky. Now, what I would like to demonstrate is what superconductors can do on the moon, as far as Hubble. This is a black stuff that you see in my hand. It's a high temperature superconductor of the yttrium barium copper oxide variety. And on the other hand, this is a magnet. This one's a magnet. Now, at room temperature, of course, this thing doesn't work. Just sit here. However, the superconductivity comes around at liquid temperatures. And this is what that is. It takes about 4 minutes for the thing to cool down, so if anybody can time 4 minutes. I find this kind of fun to do because most people haven't seen are not aware of what high temperature superconductor is. This is our telescope mechanism. And also, you see what we're doing here, constituting us a lot of smoke coming out of the mirror there. We have our smoke and mirrors demonstrating.
I have a question about this.
Sure.
Aren't you a bit frustrated? You said 77, what was it, minus 77 degrees?
77-degree Kelvin.
Kelvin is the temperature on the moon and when it's cold?
At night, when the sun is not shining on it, the temperature on the moon is about that temperature.
And that's about the temperature of this, right?
Exactly. That's
Isn't it a bit frustrating?
Why is it frustrating?
Because you're at the bottom of the temperature on the moon when you're just at the top of the temperature of the superconductor.
Not really. No. The superconductor, the temperature here of this material is something about 100 degrees Kelvin. It's about 25 degrees below.
So there is a bit of room.
Oh, the newest type is about 150 degrees Kelvin.
So you're talking about cooler.
That's right. That's why you don't have to cool it. It's up there. It's nice. It's beautiful. You just right the condition, just right. You don't have to cool it. Okay.
I wanted to know.
Yeah, here's a bunch of it.
Yeah. How did you said you can beat the smoothness of the Hubble mirror just using this form method?
Right.
Is this made with deposition? How you form with the mirror?
Okay, now the trick here is to try to, you are taking a mold, impression of a mold. Therefore, you need to get your mold polish as fine, as smooth as you can. And of course, the fact that you have to be able to get this mold smooth doesn't mean your replication is going to be that smooth. That's a little tricky there. And that is what took us several years to do. We want to be able to say that if we have a mold that's 5 angstrom IMS, we can reproduce 5 angstrom IMS. The Hubble Space Telescope, by the way, is 25 angstrom. That's why you cannot do solar planet detection.
Are you storing the, are you depositing material?
Okay, the material we use is a resin. It's coated with graphic fibers, called fiber, standard graphic epoxy stuff. But it's the nerve resin is new. It's a special resin that's developed by JPL for space structures. It's extremely stable. It doesn't throw water. And what happens when you get it is that you get it in a sheet, and the sheet is very smooth. It's not like a piece of cloth. What you do is you press it down in your mold and keep it down, and then you apply a hardener and cure it, and then stick it in the oven and cook it, and the thing becomes very hard. And then afterwards you take it off, and it gives a shape you want. That's the sample and plastic. And what you do, of course, is that the trick here is trying to get something that will allow the epoxy resin to go to the glass as close as possible, but not sticking to it. The release mechanism, that's the trick part. And that's something we took a long time to work out.
3 minutes.
Okay, thank you. Okay, now. Okay, it's done. It's cold. Let's see now. Can I borrow a piece of paper? Here. Okay, done.
Here.
This is fine. Okay. Okay, now so what you see here, I just like to show you what's happening here. Can you see this? They are not touching. Okay, there's nothing touching there. And yet this guy can spin around smoothly. And watch what happens here. Remember now, they are not touching. Now watch what happens when I move it around. Now watch what happens when I lift it up. You see that? They're still not touching, by the way.
Run the car through it.
Oh, here. Here, come on, run the car for yourself. I don't want to show you that I don't have anything on my sleeve. This is not optical illusion. Yeah, don't take your finger in there, but okay. You're not insured for that. I'm not insured for that.
Here, stick the car through it.
Okay. So the idea behind here is that you have a mechanism that allows you to point precisely. There's essentially no friction there, and yet they're not touching.
Pick it up.
Therefore, over a long period of time, there's nothing to wear out. You don't worry. I don't have to worry about friction. You don't worry about like dust, whatever it is. Nothing to wear out. You will last forever.
It's cold.
If you hold it for too long, the thing will fall apart. No, because you're out of the cooling. The superconductor is not cooling. Okay. You get cold fingers. And the trick here is that if you can make the magnet this round, then you can just spin around without any resistance. So you can just apply a pair of coils and drive it around.
Is one of the concepts that you're considering a meniscus mirror, a liquid that you're spinning that points up?
The trouble with that approach, we thought that the trouble with that approach is that you can only point to vertical. If you do anything other than horizontal, your mirror gets out of shape. And we would like to be able to scan over the sky looking at different things.
Unless you could have a very high quality flash.
Yeah, that's another point. Then you have to worry about alignment effect and everything. But we figure this way we can get a telescope and point anywhere in it. We don't need this. Remember though, your liquid mirror telescope, you have to spin it around too.
Well,
Okay, you don't just take, that's right.
That's how you get the figure.
That's right. And then you have to worry about the gears and the mechanism. What kind of bearings again? Okay, so it's the same problem, right?
How big an array would you need in order to see planets around other stars?
We need actually, if you make a couple of 1 meter telescopes about 10 feet apart, 15 feet apart, it's good enough.
How are you going to line them? Lasers?
You can use lasers to line them, or the other easiest way was just to attach them a couple of pieces of fiber optics.
How do you get the information from the far side of the moon back to Earth where you can see it?
if you we are talking about right now, we're talking about near side because we like to get communicate. Remember, we're trying to run things on the chip here, so we can get a line of sight and get some. Yes. The far side of the moon, then you need something to relay this information back. So you need an orbit stuff. You need say, an orbiting satellite or relay station. We're not into that. That will increase the cost. And right now we're trying to do minimum. We just like to keep things going, get some science going in the next few years, and get the momentum going for a lunar project. And that's what I say, if we want to put up anything on the moon, we need to long-term study what the environments are like. And this is
Who passed on this epoxy mirror?
the epoxy mirror system, no, as I said, NASA did it back in about 1960, so it's not technical stuff. Yeah. But on the other hand, what we do is what we find out how to make the mirror, how to release it properly. That is our trade secret. That is something that we took a lot of work on.
You're getting attacked.
The idea of using a thin mirror and supported by something superconductor, yes, I have that.
Are you going to be manufacturing any of these?
Yes. Yes. We initially thought that this was only for the moon. We are beginning to realize that very lightweight telescopes can actually keep their shape on the Earth quite well. And the idea of having a 16-inch or 20-inch telescope that you can just carry on with 2 fingers to observe. It's a backpack, put on your backpack and go to the doctor to observe. It's very appealing, and so we are working on that. As a matter of fact, we have there is a negotiation going between the people, our group, and the INS want to know how to make very lightweight mirrors, the telescopes that they can attach an infrared camera to, and then they can drive it on a truck easily and just go and look at the Mexican border. They are terrestrial applications. Okay. Yes.
I was wondering, you mentioned the temperature cycling problem, but you didn't mention the dust problem. Wouldn't that give you some difficulties with your lens and your drive mechanism?
Yes, we thought that. The dust, well, to begin with, the bearing, you try to get a few seal around it so the dust will get into it. The trouble with dust on the moon is mainly when you land, you kick up a lot of dust. And secondly, during the daytime, when the sunlight hits it, the ultraviolet ionizes the dust and generates a whole bunch of charge. And if enough charge builds up, boing, the dust jumps. And this happens only occasionally, but it is very prominent when the daylight line crosses during sunrise and sunset. Where you have one line, one side is light, the other side is dark. The light side is charged, the dark side is not. So a whole bunch of dust jumping back and forth. And they jump about 10 feet high, something like that. During those times, you have to keep your telescope closed. There's nothing you can do to keep it done. During the rest of the time, you figure, hey, look at it this way. Everybody has, I'm sure everybody has TVs and VCRs and computers. You notice how dusty your screen gets after a while. That's what electrostatics attracts it. So what we think is, what the telescope we're making is that we make a screen around it, chicken wire screen, so to speak, and we charge it up. So most of the time, the dust comes in, this is attracted they will acquire charge and stuck to the chicken wire instead. And they will shake it once in a while and get rid of it. That will keep the optics out. Yes?
Have you been, you say you've been given a chance to launch one of these?
No, I don't, that would be a misunderstanding. We have been selected one of the official studies for the next NASA's next generation new vision concepts for the next generation of space telescopes. That means to say they will let us study it, and it's up to us to prove our case. So, but in the meantime, as I say, if you or somebody else can come with $35 million, we'll build one. We'll put your name on the valley. Hey, that's what.
That's a cheap movie.
Yeah, exactly. The point of $35 million is a lot to you and I. Okay, most of us anyway. I'm sure there's something different. But in terms of commercial enterprise, things like that, it's a cheap movie. That's right. Yes.
Go ahead. I was wondering if DARPA had already developed some of the radiation tolerant electronics for you. I'm surprised that they haven't.
DARPA has a different application. What they want generally is something extremely small, extremely fast. So you can track a little plume across the sky. Okay, as a matter of fact, this is what they developed the CID for. But their application is generally different from ours. Ours, we want a large array. We want to be able to look at a large part of the sky at one time, study a large number of stars. And they are not interested in that. They may very well have developed about it, but we don't know about it yet. Okay. If anybody knows anything, yes. Yeah.
Your 1 meter scope is going to give you results roughly comparable to what in relation to Hubble? As good, better?
A single 1 meter telescope, the diffraction limit is 0.1 arcseconds. The Hubble can go to 0.05. So it's it's a linear function of diameter. So Hubble is twice as good. However, if I can get two 1 meters 10 meters apart, then I gain on the Hubble by a factor of 5. If I get them 1 kilometer apart, you see the point. This is beautiful thing for interferometry. So if you can space them far apart, and if they stay put, they're stable, then you get the equivalent resolution.
You're going to need something to measure the distance between them extremely accurately, right? You're going to do that.
That's right. We have to do that. That's right in the beginning. On the other hand, you only have to do it once. Once you put it down there, you stay put. And that's the thing you can't do in space, because space they don't stay put.
Well, the moon is, to a small extent, but non-zero seismically active. It would be best to have the capability to do it on occasion.
I'm sure. Well, the moon itself really doesn't cause that much problem. It's seismically dead. There's no volcano, no action there, and it's mostly surface is dust. So any vibration is in the interior of the moon, doesn't get the dust. However, you're right. Once in a while, there's nothing to stop a big meteorite from hitting the moon, just shaking everything. Up. Then you have to reposition it. The telescope we are building are designed to level themselves. They're supposed to straighten themselves out.
Will level and do the relative position measurement again.
That's right. You have to again.
How are you going to measure the relative position? Lasers or?
You have to be done by laser. Lasers.
How much is the cost of just the launch?
The launch, the cost of a Pegasus is about $15 million. So that's about as low as you can get. We can't get anything smaller. But as I was trying to say, it's a lot of fun. It's a lot of things you can do for a very little budget. Just the prospect is still bright that we can get something done. Yes.
The ESA or is there just NASDA? Are they also interested in a similar type of project?
No, ESA is interested in doing interferometry from space on the moon, but their plans are fairly definite. They haven't done it yet. The Japanese are definitely, as Dr. Borowski has pointed out, they are actually landing a couple of probes on the moon about 77 times rate, 97 times rate. But those are seismic probes. They stick them around and just measure the moon seismic motion. And about 79, this is a Lunar 8 project. In about 99, I think they're planning another follow-on, and that's not defined. But as far as we know, nobody else is doing a lunar telescope, astronomical project. Yes?
How fragile is your telescope?
Well, the way I do it, unfortunately, this thing doesn't have a concrete floor. If you have a stone floor, you can drop it, nothing happens. That's because it's really stiff. The fragility is not a problem, it's really stiff. The material will keep its shape. The what we worry about is alignment. The optical, when you have precise alignment, the mirrors have to be exactly right shape apart. That is something that you have to, we spend a lot of time thinking about.
Will temperature affect materials?
Yes, it will. So one of the things we are doing is work with folks at JPL. They have worked out a nice scheme where you use a sun shield as a shade, and then you have a bunch of inner shields with radiators in between. And then if you can point the telescope away from the sun, then you can show that, or this computer study will have it wrong that the telescope will always be the temperature at night. In other words, during day and night, the telescope temperature doesn't change by more than 5 degrees. You see, the trouble on the moon is that if you don't do it, then during the daytime, the temperature is 300 degrees. During the nighttime, it's 72 degrees. This large temperature cycling, things expand and shrink a great deal. That's what eventually will kill a mechanism. Things crack. But we think we know how to handle it.
How much would that shield add to your weight?
Very little. The shield is mostly minor. You're talking about 5 kilograms.
We'd like to thank Dr. Chen very much for a very interesting presentation.